And we're live. All right, everyone, welcome to our third installment of Astronomy on Tap Virtual, where we bring the pub, or not the pub, but rather the astronomy to you, since you couldn't come to the pub. And today we will talk about our universe, the blindfolded study of our universe. And to this end, we have a wonderful speaker for you guys today. Oliver, would you mind introducing yourself in a couple of words?
Yeah, thanks a lot for having me, everyone. I'm Oliver. I'm a postdoctoral researcher here at the Kavli Institute for Cosmology in Cambridge. And yeah, have been here for 1.5 years now. And yeah, looking forward to this.
Thanks a lot. Haley, a couple of words about you.
Hello, my name's Haley. I'm one of the organisers of Astronomy on Tap here. I'm also a postdoc in the maths department here in Cambridge, and I've been here for about a year.
Annabelle, your turn.
Hi, everyone. I'm also an organizer of Astronomy on Tap, and I'm a PhD student at the Institute of Astronomy, and also been here for about a year.
Awesome. Thanks, Annabelle. My name is Asha. I'm also one of the organizers, and I'm also your technical MC for today. So if anything goes wrong, you know who to blame. As as a final note, I wanted to say that in order for you guys to ask questions to Oliver or to anyone, any of us during the stream, please go to slido.com where you can use the hashtag AoT in order to join the event. That's where you can ask the questions as well as join in the fun of playing a real-life ISS disaster scenario simulation that Haley has prepared for you. So on that note, I would like to leave the floor to Oliver. Oliver, if you don't mind sharing your screen for us, please. Fantastic. So on that note, please, the floor is yours.
Thanks a lot. And yeah, thanks again for having me, everyone. Yeah, I'm glad to tell you a bit about my research today. So how this talk is structured is roughly, I'm going to take a bit of time to tell you the subject of my research, which is studying the evolution of the universe on the largest observable distance scales. But then the main focus is actually a bit of a reflection on how we do science and how we actual researchers try to make sure that our opinions don't influence the outcomes of our studies. And so my research is concerned with basically the two pictures that you see here, namely studying the evolution of the universe from its earliest stages to its latest stages. And what you see down here in this, I hope you can see my cursor, in this blue and red colored map, this is a picture of the so-called cosmic microwave background. So this is a type of microwave radiation that reaches us on Earth from all directions on the sky. And this is actually a radiation that is basically left over from the Big Bang. So from the very earliest times of the universe. You can think of this map as a baby picture of the universe, if you will. And what is really remarkable about this map is, so it seems very structureful if you see as the way you see it here on this slide, but as a matter of fact, the contrast of colors in this map is actually highly exaggerated. If you were to look at the actual numbers, the fluctuations in the intensity of that radiation is the relative fluctuation of these of this radiation is about a level of 10 to the -5, which means it's a thousandth of a percent. So what that means is that this microwave radiation, which reaches us from, like I said, all directions on the sky, is almost perfectly independent of that direction. No matter where you look on the sky, you find exactly the same amount of radiation. And what this tells you is that in its very earliest stages, the universe was almost perfectly homogeneous. All the gas, all the matter in the universe was distributed almost perfectly equally everywhere in the universe. Now, this is quite a stark contrast to how the universe looks today. And this is what I'm showing you in this other circle here in the right part of the slide. What you see here is a bunch of galaxies observed by the Hubble Space Telescope. And as you can see, this is not homogeneous at all, right? You have lots of very strong structures that fill our universe today, and it's very far from homogeneity. And so this is exactly the process that we are trying to understand, going from this almost perfectly homogeneous universe in its early stages to today's structure-rich universe. And so I'm a theoretician, and that unfortunately means that I can only make very primitive simulations. I have prepared a little movie for you here. What this movie is showing you as a function of time, how the density field in the universe evolves. And I've just simulated a one-dimensional universe here. And what you see on the x-axis is just some spatial coordinate. It's just along some direction in the universe, you can imagine. And then on the y-axis, what you see is relative fluctuations of the matter density in the universe with respect to mean density. Yeah? And let me just start that movie again. What this is supposed to show you is, so in the red line, I indicate the density field in the universe at very early stages. So you see the density fluctuations are actually still quite small. Since, like I said, the universe started out with actually quite small inhomogeneities. But then what happens is that over the course of the history of the universe, gravity starts to grow these structures. So for example, if you have such an initial overdensity here, yeah, then the gravitational pull of that overdensity will pull more and more matter into it, and the overdensity will grow and form a very rich structure, which you see here in this blue peak now. And this peak would exactly be such a galaxy as you have seen in that image before. Yeah. And yeah, so the question that we are in cosmology are trying to answer is, or in my area of research is, do we understand that process of going from these mild density fluctuations in the early universe to these very rich structures today? Or in other words, do we understand gravitational collapse on cosmological scales well? Yeah? And yeah, like I already indicated, we have two kind of anchors that we can look at in order to ask this question. The one is this microwave radiation that reaches us from the earliest stages of the universe. And the one is the rich galaxy structure around us today. And what we can just ask ourselves is, for example, if I just quickly, go back to this image, to this movie, what we can just ask ourselves, how, for example, does the average amplitude of these fluctuations evolve? Yeah? This is exactly what I'm showing here in this figure. This figure shows you as a function of time. So here, this x-axis you can just read as a time variable. And then on the y-axis is just the average amplitude of these fluctuations. Yeah? And like I said, in the very early universe, we start out with very, very tiny fluctuations. But then gravitational collapse will grow these fluctuations to this very rich structure that we see today. Yeah? And my research is exactly about comparing these two pictures and seeing whether our theoretical understanding of the universe correctly predicts the transition from this picture to this picture. And yeah, I will have a few more words about this figure to say at the very end. But for now, let's just move on and see how real life research in this kind of area works. And for me personally, this means that I'm working in a large scientific collaboration, the so-called Dark Energy Survey. And this is a collaboration that consists of more than 300 scientists, more than 8 countries are involved. We are observing a large fraction of the sky. We are mapping the positions of 300 million galaxies on the sky. And this is an entire company. We even have a constitution of our own. And it consists of many working groups, and there's many different working steps that you have to complete in order to finish our types of analyses. There are people who operate the telescope that you see here. There are people who remove certain image distortions from the data that the telescope takes. There are people that identify galaxies on the images from the telescope. Then other people who characterize these galaxies that have previously been found. Then there are people who measure statistical properties of these galaxies and their distribution. And then finally, there's people who compare this to theoretical models of the universe. Yeah? And for me personally, my own part in this roughly consists of the following workflow. Every day I will have 1 or 2 Zoom conferences with people from all over the world. Typically, everyone will be involved in not just one project, but several different projects. In some you might take a lead, in some you are just a contributor. And yeah, mostly we just write lots and lots of computer code. So just to give you an example, in my latest project, so far I've already written more than 20,000 lines of code. And the reason why I'm emphasizing all of these numbers is just to give you a sense that in these kind of large collaborations, mistakes will be made. If there's 300 people who all write tens of thousands of lines of code, then for sure your analysis will be flawed. There's almost no way around it. Yeah? And a big task is then to make sure that the kind of errors that you are going to make will not influence your interpretation of whatever results you get in the end. Yeah? And this is what I want to talk about in the remainder of the talk. And so to give you an idea of the kind of questions that we are concerned with, let's first have a look at how the theories of physics actually work, how theoretical physics, or what kind of theoretical models of physics are considered good models. And a prime example of this, of a successful theoretical model, is often Paul Dirac's theory of the electron, yeah? The so-called, which is given by the so-called Dirac equation. And for those of you who haven't heard of Paul Dirac yet, he has been a physicist in the early 20th century here in Cambridge, at the institute where Haley is also based, for example. And what's so astonishing about Dirac's equation is this equation was predicting a particle which was up until then not yet known, the so-called positron. Yeah? So the existence of the positron was just postulated out of this equation without anybody ever having seen that particle or having heard of it or whatever. And then just a couple of years after he proposed this equation, this particle was indeed found, and this was considered a major confirmation of Dirac's theoretical work. Now, this is the usual lore of the story, but I would like to add a certain point of view to this. To me personally, what's so impressive about this is not that Dirac was able to predict something that nobody had yet seen, and then this thing was indeed found. What, in my opinion, is so impressive about it is that Dirac wasn't thinking about the positron when he was deriving his equation. Yeah, he was thinking about the electron, which is the antiparticle of the positron. And yeah, the electron, as you may know, is this little particle that basically makes up our electric current. Yeah, if you turn on your light and or any electric device, then it's basically electrons moving through your cables that make up the electric current. And so what Dirac's intention was, he was actually completely blind to the right side of this figure. He didn't know about the positron. He just wanted to find an equation that correctly describes properties of the electron that couldn't yet be properly described within any previous theoretical framework. And it turned out the only way he was managing to do so is to come up with an equation that also demands that there be a second particle. Yeah? And this is really what I personally find so impressive about this, that he was only thinking about the left-hand side of this figure and nevertheless found what's on the right-hand side. Yeah? Now, unfortunately, this is, to be honest, sometimes quite different in modern cosmology. Yeah? So in modern cosmology, all that gravitational collapse that I was talking to you about before mainly follows the laws of Einstein's general theory of relativity. And this theory is very well tested today, at least at distant scales of the solar system. So the way the planets and other bodies in our solar system move is in perfect agreement with Einstein's theory. And it's a theory that's very hard to, it's very hard to imagine any deviations from that theory that wouldn't completely destroy our solar system. Yeah? And how the workflow in today's, in some theory departments of today's cosmology actually is people try to come up with theories that that actually try to, whose main purpose is not to predict something that is some already done observation, because all the observations that we have made so far are in perfect agreement with the existing theories. But instead, they want to come up with theories that don't change any predictions for the existing observations, but make some interesting predictions for upcoming observations. And then they hope that once we make these upcoming observations, one of their theories will be right. Yeah. So this is, of course, I'm exaggerating here a bit, but yeah, if you wanted to be cynical, then this is kind of how you could depict some theory work in today's cosmology. And the problem here is that the proponents of all these different theories are actually now not blind to the right-hand side of this slide anymore. Yeah? And this in particular holds the risk of something that is called confirmation bias. And to understand how confirmation bias works, I just want to give you the following thought experiment. Yeah? Imagine you carry out any sort of cosmological analysis, or as a matter of fact, any scientific analysis. And as I told you before, in these huge collaborations, many mistakes will be made. Yeah? So imagine that in your analysis, you make 10 mistakes. Yeah, in your computer code, there are mistakes, or some assumptions that you are making are wrong, or whatever. So you make 10 mistakes, then you look at the results of your analysis, and you really don't like it because it doesn't confirm your favorite theory that you wanted to see confirmed with your analysis. Yeah? Then what you do is you go back to the drawing board, you look at your analysis, at your computer code, and you try really hard to find all the errors that you have made. And then you find 5 out of these 10 mistakes. Then you go back to your data, you redo your analysis, and ta-da, you get the result that you're happy with. Yeah? And immediately you write a scientific publication, you publish it in some journal, and you don't think about all these other 5 mistakes that are still lurking in your analysis. You know? And this is, in a nutshell, what is meant by confirmation bias. And this thing you really have to be aware of. And we are aware of this in the Dark Energy Survey collaboration, and we are trying to prevent this. And the way we are trying to prevent this is by a so-called blinded analysis. Yeah? That means when we are doing our analysis, we try to be as ignorant as possible to the potential outcome of our analysis. And so just to give you 2 examples of how people in real research have actually tried to implement this is, so in a competitor collaboration of the Dark Energy Survey collaboration, what people do is they literally have one true data set measured by their telescope, and then they will have 3 other false data sets that are completely made up or coming from simulations or whatever. And so how this literally works is that this collaboration, they perform their analysis on all of these data sets, the true data set and the false one, and only one person knows which of the data sets is the true one. And then these teams have to write literally a scientific publication for all of these data sets for whatever outcome they get in their analysis from all of these data sets. Once they have finished these publications, that one person who knows which is the true data set tells the rest of the team which it was, and that paper has to go to the journal without any further changes. This is how that so-called kilodegree survey team is doing their work. On the other hand, we in the Dark Energy Survey, we have a slightly different strategy. For us, it's literally the following, or at least for our year 1 analysis. It was literally, we took our data and certain quantities in our data were just multiplied with a random number. Yeah? And only few people knew about this number. Yeah? And so that basically means that we couldn't ever compare our outcomes of our analysis to whatever expectations we had, because we knew that data is anyway falsified by some random false factor. Yeah? And again, we have to perform our analysis. We have to carry out all the tests we possibly can to make sure that we don't have any errors in our analysis. And only once we agreed on all our tests, those people that know about this random number would actually reveal it to the rest of the team, and then you have to undo it. And yeah, this is kind of what I'm trying to describe on this slide. Again, like I said, in the middle, you see all of these different steps that you have to do in order to carry out such a huge analysis. And the idea is, again, you are trying to be blind to the right-hand side of this slide. And you're trying to look only at theory independent, or I should rather say expectation independent tests. So what this forces you to do is you have to look at your data and come up with all possible tests that you can do, consistency tests that you can come up with in order to, that are independent of your expectation, but that can still tell you about whether you are doing something wrong or not. And this really sparks creativity, if you will, because it's kind of, like I said, once you, as a team, you decide, okay, we have done all the tests we can, we have made sure as much as humanly possible that there's no significant errors in our analysis. Once you get to that stage, and once you get to the so-called unblinding, where people tell you about this random factor and you can undo it, then you are forced to do your analysis and publish it without ever reconsidering it. Yeah? And yeah, this brings me to my last slide. And yeah, I just wanted to get back to this figure. And what you have to imagine is now really the following. This blue line that you see here, again, this figure shows you as a function of time how the amplitude of density fluctuation evolves. And this blue line that you see here takes results from the so-called Planck satellite, which was measuring exactly that early universe microwave radiation. And so the blue line shows you a theoretical extrapolation of what the Planck team found for the early universe to today's universe. And the orange band, on the other hand, is exactly what the dark energy survey, so what the team I am involved in, was measuring. They were looking at the late-time universe, at the galaxy field around us, and trying to actually measure what today's density, amplitude of density fluctuations is. And what you should really imagine is that we didn't know about what the amplitude of the red line would be, because, like I said, it was multiplied by a random factor. Yeah, so there's a real fear that that your analysis will be way off from what that other experiment predicted. No? So, for example, you could imagine this orange band being, for example, way down here. Then, in principle, following our rules, we would still to us, it would be very obvious that we had made a mistake, but we would still be demanded to publish it this way in order to not fall into any confirmation bias. Yeah? Well, as you can see, fortunately or unfortunately, I don't know, this orange band is not way down here, but it is also not in perfect agreement with that other experiment. And yeah, that is exactly the outcome of this blinded analysis that we did. And it's actually quite an interesting result because, yeah, like I said, it's not like we have perfectly disproven our theoretical understanding of the universe, but there are some hints emerging that we may not understand gravitational collapse on cosmological scales. And in addition to that, we can be quite confident that this orange band isn't the result of any confirmation bias or anybody's expectation going into that analysis. And yeah, that's all I wanted to say. Thanks a lot, everyone.
So thanks a lot, Oliver.
All right, Asher is muted, so I'm going to say thank you so much for that, Oliver. That was fabulous.
Then,
do you want to try again now?
Yes, I am all live now. The funny thing is that I can mute myself independently for the stream and for the Zoom, so everyone could hear me, but you couldn't, which is funny. All right. So if you don't mind holding your slides open for a moment. Oliver, because we've got questions coming from the audience. So
Oh,
on that note, I'll ask a couple of them. So let me real quick switch to them so that everyone else can also see them. You won't see them, but everyone else will. So you're disadvantaged. Now you have to listen to me. Okay, so we've got the first question coming from Brian, who asks, if the universe expands, does it mean that the microwave background shows pieces of the universe we cannot see now?
yeah, that's a good question. So it really depends on how you want to see it. So we can see those pieces of the universe because we receive that microwave background radiation, but we can't see how those parts of the universe look today, indeed, yeah. If we wanted to see how those parts of the universe look today, we would have to wait several billion years for light from those distant parts being emitted today and reaching us in that future. So indeed, we can't see how those parts of the universe look today, yeah.
All right, so we've got Brian's question down. Then we've got an anonymous question that's, I think, more of a personal nature, or say work environment nature. And the question is, does working in a collaboration mean you can never make a discovery by yourself, and can you win a Nobel Prize?
Yeah, so how that typically works is that the Nobel Prize, if a collaboration would discover something very spectacular, then typically the Nobel Prize would go to that entire collaboration, I guess, or at least to the team of people who originally proposed and designed an experiment. So in that sense, yeah, it's hard to make discoveries just on your own. But then on the other hand, what you can imagine is that there's always a huge driving project that drives such a collaboration. So for example, you want to measure these amplitudes, like I said. But then if you have data on 300 million galaxies in the universe, there's lots of other different interesting questions that you might ask to that data. And there's lots of room for individual people or small teams of people to propose smaller projects, which can still have very interesting outcomes or results.
Right, thanks a lot. If you don't mind responding to a couple more, we've got someone on YouTube. First of all, we've got someone with the nickname GT Talera saying that it's a comment saying that it's clever bias proofing for sure. So I take that as a compliment for the collaboration. And then we've got Ivo Gurski, who is asking, is it possible to use little black hole to earn energy from the accretion disk of another black hole? So it might be off topic, but if anyone is willing to take it up, including you, Oliver, then please take it away.
Yeah, I'm not so much an expert, but I feel, Haley, you might actually know more about this.
I can try. So I'm guessing that the question is asking whether we can harness the energy from a little black hole, which is feeding off another black hole. So I think this might be, I was actually reading about this the other day. So it's actually not the other day, last week. So it's actually quite lucky. It's about black hole bombs. So these are the things that like basically, oh God, I can't remember. It's kind of like a Dyson sphere. So those how we like put those, well, we don't do this, but like really advanced civilizations would like encompass an entire star in basically solar panels, which would like bounce around the light and generate energy. And then we'd like extract it and use it to power our planet. And I think you can do a similar thing with a black hole. I'm not sure exactly how it works, but you can put something to encompass a black hole. And I think maybe something to do with Hawking radiation. I don't know. I'm just throwing buzzwords out there now. So I really have no idea. I tried.
Yeah, I mean, I think there's one thing that I maybe can say, which is somewhat intelligible. Despite again, I'm not at all an expert in this, but so if you would have a black hole spinning and eventually merging into another black hole, then I think you don't really get an accretion disk from that or anything. But what's being emitted is actually huge amounts of energy in the form of gravitational radiation. So there's one number that I remember in that first black hole merger that has been found by the LIGO experiment. Calculations showed that energy has been released in the form of gravitational waves in the amount that corresponds to 3 solar masses. So 3 times the mass of our sun, completely converted into energy. And that was released in terms of gravitational energy. So I'm not sure how one would ever harvest that energy, to be honest. But there is energy that's being released for sure.
Yeah, and I think we probably could if we were advanced enough. I don't know about gravitational waves, but maybe some kind of Hawking radiation or something. I don't know how to harness gravitational waves personally, but maybe there is some way to do that in the future when we're more advanced.
Yeah, so that's the beauty of those events, that you can be struck with an absolutely random question.
Absolutely love it. Keep them coming.
Okay, so actually we have something. There are 3 more questions, if you don't mind, Oliver.
Sure.
So we've got a question from someone called Dato. And the question is, how much time passes between the 2 pictures you show? I assume this is the last slide that you're showing right now, because the bottom is, of course, in terms of redshift. So roughly how much time is it in, I guess, human intelligible numbers?
Yeah, it's so it's at the very least 10 billion years. So this picture is actually not from today's universe. It is somewhat in the past as well. So the picture that you see on the left is 13 billion years old. And that picture, I don't even know how old it was, would be, but there's about 10 billion years. So that would be twice the age of the Earth is between those 2 pictures.
Right. Thank you. I hope it answers the question. Then we have a question from Anonymous. And that's, I think, philosophical. And the question is, does the problem with the bias mean that we cannot trust anything the astronomers say apart from the dark energy group?
No. Like I said, the kilo degree survey also employs a blinding strategy. So you can trust both of these surveys. But no, it's not just something that we invented. Nowadays, all cosmological analysis try to incorporate some sort of strategy like this. So it's something that really only picked up over the last 10 years. The triggering factor was really that cosmology was starting to become a quantitative science. So in the 80s and 90s, it was mainly just qualitatively confirming certain aspects of cosmological theory. But over the last decade, we have really collected huge amounts of data so that people had to start thinking, be more careful about these kind of things. And so today, I think all larger cosmological analysis employs such a strategy. Right.
So I guess the answer is, yeah, we can trust other astronomers too.
Yeah.
But that was pretty tricky. Thanks for that. And we've got a final question coming from someone called Juni. And the question is, that's clearly someone who's into the topic a little bit more. It looks like the density profile changes shape around redshift 1 or 2. Can we see the signature of this in observation?
Yeah, so this actually, I assume what this question is referring to is the fact that the growth of structures is kind of flattening out here. And so there's 2 explanations for this. One is really that what I'm using as a time variable is cosmological redshift. And this is actually, unfortunately, not linear with time. So you can't really think of this as being just as time just linearly evolving over this axis. But at the same time, it is actually true that the growth of structures is slowing down at the late universe. And the reason for this is exactly, unfortunately, I think probably not all people have heard of this, but researchers have found that the expansion of the universe is actually has been accelerating in the last few billions of years, and what's happening is really that ever since, say, 2 billion years ago, the expansion of the universe has started to become faster and faster and faster, and it is too fast in a sense for structures to collapse anymore. The universe is being stretched apart faster than structures can collapse under their own gravity. So in that sense, there is some truth to this curve flattening out. And this is actually such a good question to end this session with, because what people think what is causing this accelerated expansion is a mysterious substance in the universe which people call dark energy. And this is exactly what the dark energy survey was meant to investigate, actually, how dark energy behaves. So exactly this turning point where the growth starts to flatten again, this is where the exact properties of this mysterious substance would be most influential. And this is exactly the period that the dark energy survey is trying to investigate and find out what exactly is going on. So in that sense, for example, the survey I'm working on is exactly trying to measure this bend. And yeah, so far we only completed our year 1 analysis. Overall, it's going to be 5 years. So we can't yet say anything totally conclusive about this, but this is actually exactly one of our science goals.
Awesome. So on that note, I think it was, as you said, it was a brilliant question to end the question session on. So on that note, I would like to ask you to stop sharing your screen at the moment. Thank you very much. And we will move on to the game part of our meeting, which you are most welcome to participate in, by the way, Oliver. So if you want to check it out on slido.com, please feel free to do that. And for people in our stream, we are going to move into the game directly. So, Haley, would you like to take it away from here?
Sure. So this is a bit of a trial run for a game, I guess. So this is we wanted some way to let everyone know all of the different interesting ways that you can die in space. And we thought this is probably better to do in October for Halloween, but whatever, we're doing it now. And we thought it would be kind of fun to do like a kind of choose your own adventure-esque kind of game. So it's going to be along those lines. And basically, I'm going to tell you a story about your lifelong dream to be an astronaut and all of the things that could possibly go wrong, spoiler alert, go wrong when you're on the ISS for the first time. And so basically follow me along on Slido. So if you head to Slido, if you're not there already there, and please do participate because I'm really curious to see what you guys think along the way. And most of the stuff I'm going to say is true and is based on either real events or a hell of a lot of Googling that I did about how stuff works on the ISS. So if you have any questions about how that stuff works, then also ask them on the Slido part too, because I might be able to answer that. But me and our other organizer, Johnny, had a bit of fun discussing this story and making up this scenario. So he can't join us tonight, but all right. So are we good to go with the slides, Asha? Awesome. Okay, so I'm assuming we're on slide 1. All right, so let's start. So your day has finally come. After 2 long years of intense training, you've made it. You're an astronaut. You've learned Russian, you've learned how to fly a jet, you've experienced weightlessness in many different ways, mastered orbital mechanics, learned how to give CPR in low gravity, and had your appendix and wisdom teeth out just in case. But basically, it's been a lot of work, but you made it. It's launch day, and you're strapped into your seat next to your favorite crewmate. Life couldn't be better. You're extremely anxious, nervous, queasy, ecstatic, sweaty, emotional, and amazed all at the same time. You've been strapped in for almost 3 hours now, and you go over the final checks once more and let mission control know that everything is in order. Your mate gives you a thumbs up, and it's all systems go. You can hear the countdown beginning, and you feel the ship rattle and shudder as if an earthquake is tearing through the launch site. It's the main engine igniting mere seconds before the rocket boosters ignite and you begin accelerating to 2.5 Gs. As you reach 40 kilometers above the Earth's surface, you've disconnected from the main rocket body and the ship is now much lighter, meaning it's easier to accelerate. You reach 3 Gs for a solid minute and it feels like 2 of your fully grown mates are standing on your chest. Your speed rises above 13,000 kilometers per hour. The main engine cuts out and the orbital module separates from the ship. The acceleration pressure vanishes and you start to float in your seat, 220 kilometers above the Earth's surface. You've lived to make it to orbit and to start your mission at last. It was an exhilarating sense of physical and mental relief at the passing of that risky phase of liftoff and ascent to orbit. So now it's been about 2 days since liftoff, and your orbiter is approaching the ISS. The delicate automated docking procedure begins. And after finally making it on board, you slowly settle into life on the International Space Station. Even simple things like brushing your teeth, going to the toilet, and exercising are now totally different. You were prepared for this though, so you quickly adapt to life in low gravity. It's been a few weeks now of normal space activities when your crew gets an unexpected, urgent message from ground control. They tell you that a large solar flare was just observed on the surface of the sun. You have less than 1 hour until the potentially harmful particles from the coronal mass ejection intersect your path. The Earth is normally protected from these particles because of its magnetic field, which deflects them. But in an hour, the ISS will be passing just outside of Earth's magnetic field, so it will be exposed to the harmful radiation. Ground control warns that communications might be interrupted, so they want you to think of a solution fast. What do you do? And this is where you guys come in. What are you going to do?
Yep, exactly. So from a technical standpoint, if you're a part of Slido, and I know people are because I can see the answers coming in, and you will be able to see them soon. Yeah, there we go. I've shown them to the audience as they're coming in. Yeah, so please take it away and give us your responses. So far, Haley, how much time do we give for this life-saving answer?
Yeah, I don't know. Give him a little bit of time just to kind of see if it changes anymore. But I'm curious. This is an interesting one because, I mean, I think it's a bit of a trick question. I don't think it's exactly what you expect. I don't know. What would you do, Oliver?
Yeah, I have no idea, to be honest. So I mean, if I were to fly to the ISS, I would probably ask beforehand whether people have prepared for something like this. I don't know.
Ruining it.
Guys, you can't see the results, but the audience can, which is hilarious. And actually, we have an equal split.
Oh no, I can see it too. Oh my God, we do. Okay, so a third of you think that we should build a protective fort out of oh no, there we go, it's changing. All right, I'm just gonna.
Yeah, that was my vote now.
So now we know what Oliver voted for. Good.
Awesome. Okay. All right. I think we should we cut this here? So it looks like the majority of you think that it's not a problem. Don't worry about it. The ISS is totally protected. This is not quite right, actually. So the correct answer is A. So good job to the few of you who picked that one. And I'll just give a bit of an explanation for this. So A is actually correct. And this is actually the procedure that is implemented on the spacecraft. So you basically just surround yourself by as much mass as you possibly can. And the reason for this is that adding all this mass around you means that the particles lose energy as they move through that mass, and then they're less energetic when they get to your body, and so they're less likely to harm your organs and stuff. So B is probably a maybe. It would probably be fine, but the ISS does have a protective shielding around it, but there are thinly shielded areas of the ISS. So if you just so happen to be near one of these thinly shielded areas as the particles go through, you would be at risk. So it's probably not the best idea. And C, this just doesn't exist. We totally made this up. There are no radiation blinds on the ISS. And the reason for that is also interesting because something like a radiation blind would really only have one purpose. And this is something that they don't like on the ISS because you've got a ship, you've obviously got to fly it up from Earth. So you've got to fly this big heavy thing that only has a single purpose. So they try to make things multi-purpose that they send up to the ISS. And unfortunately, they haven't found another purpose for radiation blinds, but maybe someday they will.
Can I just mention that as you were revealing the correct answer and it was highlighted in the system, people decided to change their mind as well, which is a funny effect that we seem to have seen in other live events as well. So yes, now we've got an equal split between build a protective fort and don't worry, the ISS is protected.
Some people still think we should close the radiation blinds though, so I'm done with that.
All right. So I guess we can carry on with the story. Thank you very much.
Yeah. And have we got the, I can't see, but we've got the image of the two women actually shielding themselves. So this is a trial run of, I think it was Orion, where they were kind of practicing the radiation procedure. So as Oliver said, you would already know what to do if you were actually on the ISS. But I'm more interested in what you guys think you would do without any training. Anyway, all right, so let's throw ourselves back into the narrative here. So our protective fort worked perfectly. And after waiting out the solar storm and getting the okay from ground control, you and your team put all of the protective supplies back in their places, and it's time to get back to work. But a few hours later, you'll receive another message from ground control, but this time much less panicked. They tell you that the energetic particles from the solar storm seem to have interfered with one of the GPS satellites in orbit and thrown it slightly off course. It looks to be heading towards another satellite and they could collide. But they tell you not to worry, since the GPS satellites orbit at 20,000 kilometers above the Earth. They're really far away, much higher than the ISS. So it's incredibly unlikely that you'll be in any danger. But regardless of this, you're nervous. You all know how dangerous even a tiny piece of space can be when you're hurtling through space at nearly 28,000 kilometers per hour. And then your crewmate Tim shows you a picture he took of a crack in one of the windows in the ISS, which was most likely caused by a tiny fleck of paint. So that's that image you're looking at right now. That is literally a crack in the window in one of the modules on the ISS. Good thing they're quadruple glazed, but you still didn't think this was the right time to bring it up. So not long after that, ground control calls again and tells you to adjust your orbital height since the satellites have collided and the debris is heading straight for you. They say to act fast since there might already be fragments of the satellites too small for them to detect close by. Just as you end the call and start the engines to move up in orbit, you hear a large crash and see sparks flying out the window. Oh no, they've hit Canadarm. The giant robotic arm on the ISS used to move supplies around and help you when you work in space, perform external maintenance, but a piece of debris from the satellite collision has hit the arm, rendering it useless. What do? Do you go out and fix it now? Do you wait for the debris cloud to pass and then go out and fix it? Or do you leave it because we don't really need that kind of arm anyway? Okay.
I like how you put stress on we don't need it anyway.
It's not like it was made for a purpose or anything.
Yeah, that was exactly my response when I of course I know the correct answer, so I'm not playing the game, but that was my first thought when I saw the script. I was like, yeah, they probably made it for a reason, so maybe let's try and fix it. But yeah,
I'm honestly glad to see that no one thinks that we don't need it, because it would be pretty pointless to ship this giant mechanical arm up to the ISS when we don't actually even need it. So,
actually, as you were saying that, I forgot to switch on the Slido window, so I'm terribly sorry to our online audience.
Oh, okay.
You couldn't see the answers coming in real time. Apologies about that. See, you can blame it on me. I'm the technical MC here. Yeah, but truth be told, we've got actually an overwhelming response of people saying that they should wait for the debris cloud to pass and then go out and fix it.
Fabulous. You guys would make brilliant astronauts. So yeah, this is correct. So as someone or some people, 14% has said go out and fix it now. So that would probably not be a very good idea, because there is all this debris hurtling towards you, and your spacesuit might get ruptured if you get hit by a piece of debris or something like that. So this is not really what you want when you're out in the vacuum of space. So we're going to go.
Canada. Maybe you have patriotic feelings about it. I don't know.
Hey, Annabelle.
If you're from Canada, I mean.
Maybe she does. I don't think she can join us at the moment, but I'm sure she would have some kind of attachment to the Canadarm and want to get out there ASAP and fix it. But
yeah, I can chime in. We need
cool.
that arm. Very important.
Awesome.
Sorry.
I'm glad that you feel that kind of attachment to an arm. So it is correct that we do need the arm, so please don't leave it broken. So what we're going to do is we're going to wait for the debris cloud to pass, and then we're going to go out and fix it, which I think is probably the best thing to do. Although it is important to note that the debris storm could have a long unknown duration. So we don't really know when this thing is going to end. So you're probably going to have to wait quite a long time just to be safe. So now we've done this, we've waited a reasonable amount of time and also adjusted our orbit as ground control told us to. It doesn't seem like there's any more space debris nearby. So it's deemed safe to head out and fix Canadarm. You put on your spacesuit and prepare for the spacewalk. With your crewmate at your side, you venture out into space to fix this vital piece of machinery. You make it out to the end of the arm. Are we on the right side?
Yes, it's just the video is quite long.
Oh, it's fine. Just skip it. It doesn't matter.
Okay. Okay, fantastic.
It was just illustrative. Awesome. So you make it out to the end of the arm and you identify the damage and start work on the repairs. While fixing the space arm, you suddenly feel a sharp pain in your eye and tears start forming. But in the low gravity, they don't fall down your face like they normally do. Instead, the tears form a layer of liquid across your eye that you can't blink away. And it stings, so you think there may be a toxic gas leak inside your suit. You can't see at all. What do you do?
Yes, and we've got now we've got the answers shown in real time, so I'm really excited to see what people think. Yes,
Fabulous.
Also, let's not forget that we have a little bit of an offset between what we say and what the audience sees.
I remember. So this is a really interesting one, and I love it because this literally happened to someone on a spacewalk. So this is not giving away the answer, but this is a real scenario that actually happened to someone called Chris Hadfield, who is a really famous Canadian astronaut. And this sounds absolutely terrifying. I can't imagine being on a spacewalk out in space anyway, but let alone in this giant helmety thing, and then your eye starts hurting and watering and you can't see anything. It just sounds like bloody terrifying, to put it straight. Okay, so it seems like a lot of you think that we should just feel our way back to the airlock where you can remove your spacesuit. Some people think that we should release the air from our spacesuit to try and vent the toxic gas. More people are thinking that too. But no one is so far as saying just keep going. It's probably an eyelash. So that's good, because you don't really want to kind of push through with this kind of thing if your eye hurts and you're trying to fix vital machinery on the ISS. So I'm happy to have that solution. Oh, someone does. Okay.
Just as you mentioned that. And remember that there is a delay. So they probably clicked it the moment, just moments before you said it.
Well, that person probably shouldn't be an astronaut. I'm sorry. I'm just kidding. This is something that keeps you in training if you do want to be an astronaut.
Oh, okay. They've changed their answer. That's fine.
Oh, it's good. This is all about learning.
Right. Since I've highlighted the correct answer, can you please tell us why?
Okay, so the majority does think to release the air from our spacesuit to try and vent it, which is exactly what Chris Hadfield did, which was absolutely amazing. This is back in 2001. And it turns out the irritant in his eye was a leak in the anti-fogging kind of part of the visor, because they have these big glass visors. So they need to keep them not fogged, kind of like how you like spit in your goggles before you wear them. But what they use is a mixture of oil and soap. So that leaked into his spacesuit and the soap got in his eye, which stung it. And this is crazy. So he vented out, so the gas kind of went out of his, vented out the air, got new lot of air in it, and just kept on working like an absolute boss. So letter A is wrong, because what we don't want to do is, if we can't see and we're trying to feel our way back to the space station, something that I learned writing this story is that there are parts of the ISS on the outside where there are no touch zones. This means that there are sharp edges which could potentially tear your spacesuit. So if you're not looking while you're trying to feel your way back along, you could put yourself in danger by tearing yourself and exposing yourself to the vacuum along the way. And C is, we're not saying that we should do that, because it's very difficult to blink the tears away when there's no gravity. So they'll just kind of sit on your eye and sting, and you won't be able to see very well. So that's not something that we're really interested in. Okay, so we did well. We vented the small amount of air out of our spacesuit to kind of refresh it. Good thinking, good job. And it does, as I said, it turns out this was a leak in the anti-fog solution used in the visors, and this solution was stinging your eye. So you make a mental note to recommend that we switch to baby shampoo instead of soap, and you carry on working. So it takes hours to finish the repairs, and it was grueling work, but you and your crewmate finish it off with a space high five and head back to the airlock. You're both exhausted. While pulling yourself back alongside of the ISS with vision, so you know where not to touch, you suddenly lose grip and start drifting away into space. You are tethered to the side and you think it's holding firm, but now you have to get back to somewhere that you can hold on to. So what do you do? And I believe the video that we have right now is a quite violent representation of what, of what this is. So it's not quite that violent. This is from Gravity. So do we wait and one of our crew members will come and assist us? Do we use our little jetpack to steer ourselves back to the ship? Or do you pull yourself back in using your tether? So let me know what you guys think. Again, this one is maybe not so much a trick question, but.
As I've said, we've got a little bit of a delay, but we've got the first response in, two responses in, both of them being use your jetpack to steer yourself back to the ship.
Interesting. Okay.
Oh, someone voting for the tether.
No one wants to wait around in space and see if someone's going to help you. Although I think if you had the problem like the person in the video, I think you would probably be a little bit disoriented, but this is a much milder case. I
like how he said you'll be a little bit disoriented, and we've got a beautiful close-up on Sandra Bullock coming into the screen. This is beautiful. I really, really like that. Oh God! Oh no! Who's that? Is it her flying away? Is that her? I think it was her. Oh my God!
Isn't it?
Oh. Oh, that was really sad.
Okay, yeah.
Yeah, when you're flying into the darkness, that was really not okay.
No. Anyway, it's not that bad again, it's a dramatization.
Yeah, of course.
Okay, so some of us think that we should wait it out and get one of our mates to come and help us, and otherwise we're pretty much split. Well, not anymore, but we were split. Most people think we should use our jetpack, and now we're split between waiting and pulling ourselves back in. So I don't know if there are two right answers here. Yeah, and I mean, the first one is probably fine as well, but you don't really, we know that our other mate is also exhausted from the spacewalk and from fixing it. So they also might put themselves in danger if they come to rescue you. So since it's such a mild scenario, we can get ourselves out of this. So the only thing I want to say is with the jetpack, there is a bit of a risk of overshooting. So if you accidentally, your tired thumbs or fingers or whatever, accidentally shoot yourself too far, then you might knock yourself into the ISS. There's a bunch of things that could go wrong there. So the safest option is to just pull yourself back in using your tether. So now you all know. Okay, so we've used the very last of our energy to pull ourselves to the safety of the side of the ISS, and we can continue making our way back to the airlock. You've never felt so exhausted or relieved to be back safely. So now, in celebration of surviving the day's hazardous events, the crew breaks open a tube of space vodka. One of your fellow crew members ends up having a few too many and starts floating erratically towards a critically important science experiment nearby. You push off the floor of the station to propel yourself towards them, but you're feeling quite woozy yourself, so you veer off course a little bit and start flailing your arms to try and reach your crewmate. They see you, think you're going in for a punch, so they grab you and start to fight back. You're caught in a tangle in low gravity, tossing and turning and trying to wrestle each other off, but only making matters worse. You feel sick to your stomach and try to grab onto something nearby to stop the violent tumbling, but it's too late. You can't hold it in anymore. You vomit. Without gravity, tiny pieces of your chunder float and disperse all through the ISS in all directions, some moving towards the precious instrument panel. What do? Do you tell everyone to hold on so that you can open the door for a second and flush it out? Do you leave it because the ISS was built to handle small chunks of vomit in the control system anyway? Or do you yell at your crewmates to help you grab all the tiny pieces of chunder before they get stuck? Get your crewmates to help you.
Let me show the responses. Being the technical MC, I must admit, I've got a little bit carried away with the slides, so I'm really sorry, Haley. If you watch it later on, please don't be too harsh on me.
I'm sure it's fine. Excellent. Oh, some people think we should open the door. I'll leave it behind. So I do just want to disclaimer. I don't know if there's a right answer to this question because I don't think this is ever going to happen. So I will explain this later, but this last scenario was totally made up, and I thought it would be fun to end on a kind of crazy note, I guess. So how are we doing?
So I think
beautiful. So we've got the right answer to get everyone to kind of help you clean up everything quickly. But you know, we've all made some mistakes when we're drunk. We've all made terrible decisions while we're drunk. But this time was something else. Even though C was the last one was the right answer, you decide to go with the first one. You think if you just open the door for a second, you'll all be okay and the vomit will be sucked out, because you know that human beings can survive being exposed to vacuum, if only for a short time. So luckily, the main door is right next to you. You reach out and you pull it open, and the precious air inside the ISS shoots out as you lose your grip on the handle. You know you have about 5 to 10 seconds to close the door before you fall unconscious, but the vomit rapidly shooting past your face distracts you for just long enough. You know you shouldn't hold your breath, since any air held in would rapidly expand with the drop in pressure, rupturing your lungs. You violently exhale as quickly as you can and attempt to avoid this, and start to reach towards the door handle, trying not to let go of the rail you're holding with your other hand. You feel the saliva on your tongue start to heat up until it reaches boiling point. Your eyes start to feel gritty, as if the liquid surrounding them was bubbling. You look down at your body and notice that your arms and legs are growing in size, almost doubling. The water inside your body has begun to vaporize, causing the tissue beneath your skin to swell. It is too late now, and as you feel your grip start to loosen slightly as you lose consciousness and drift off into the emptiness of space. The end. You're dead.
I shall have the pleasure of putting you out of my misery.
I thought you were going to ask for last words or something.
Nah, that would have been good though. But you're too busy like dying from the vacuum of space to worry about that kind of stuff. But so as I said, that last scenario was totally made up and not meant to be realistic at all. So I just want to go through some of the reasons that it was totally made up, so that hopefully we can understand that stuff that I said at the last bit was not real. So everything up until you got drunk on the ISS was meant to be a realistic representation of what it's like to get into trouble and what kind of solutions they come up to fix that kind of stuff. But the last one is wrong for a few reasons. The first one is that alcohol is strictly not allowed on the ISS anymore. So some of the earlier Russian cosmonauts used to be sent into space with small amounts of cognac and vodka on doctor's orders. And, you know, for example, Buzz Aldrin drank wine on the moon, so poured it into a glass on the moon and drank it. And some alcohol is sent to space for science experiments, like how to brew beer in zero gravity and like all this kind of stuff, but not for consumption, which makes sense because you wouldn't want like your airplane pilot to be drunk, and you wouldn't want them to be fighting and vomiting and opening doors because they're drunk. Another thing is that I don't know if the vomit would actually go all over the place, because I mean, I'm sure we've all seen some videos of how water behaves in low gravity. So you kind of get these like, they holds together because of the surface tension of the water into kind of these like blobs that kind of just float around. So not to get into too many details, but I'm sure it would depend on how liquid your vomit is. But we'll just stop there, that I'm not sure it might need to be knocked to be, you know, spread all over the place. And probably one of the most obvious ones is that there isn't just a door to outer space that you can just open. It's very difficult and very controlled to actually go out into space from the ISS. So there's an airlock. And so what this means is you go through one door and then you close the door in your spacesuit. And then that little region has a door to space and a door to the ISS. And in that region, they depressurize it while you're in your suit. And only once it's depressurized can then they open the door out to space. But once that airlock is depressurized, this door back inside literally cannot be opened. Like they've safeguarded it. So there's no way that you can just open the door to space.
Yeah.
So
funnily enough, it was actually shown in the James Bond movie, because as they were moving past, the main character shot the villain, who was then put in pressure.
Yeah, that was the last video that we saw, right?
Yeah. So as you were talking about water, I also showed again the video about water droplets in the space station. So that's pretty fun. And we have a comment from someone called Jamrat on YouTube, who says, "I'm dead no," which is really sad. But last words are, "Oh no." So that I think answers Oliver's question about the final words.
That is true, but to say that, you would need to suck in air, and being in the vacuum, that would mean that your lungs would rupture because all the air in your lungs there wouldn't be any air. So I don't even know if you could talk.
Well, maybe you can also use sign language.
That's a good one. You're so ableist. Thank you, Oliver. Fabulous. So maybe we should all learn the sign language for "oh no," just in case we're stuck in this situation one day. That's a top tip.
Yeah, very probable. All right. On that note, everyone, I think it's a good time to wrap up. And thanks, everyone, for joining us today, for playing the game with us, having fun, and most importantly, thank you, Oliver, for the brilliant talk and for answering all the questions from the audience. And on that note, let's just say goodbye and see you, everyone, in October. Bye.
Bye.
Bye.